Hi, everybody. In this video lesson, we're going to continue talking about the particle theory of light by looking at an effect, an experiment that actually gave experimental evidence that we can think of as light as a particle. We call those particles photons. Those photons have a specific energy dependent on their frequency. So let us get started. Just to summarize, we talked about Planck's work solving the ultraviolet catastrophe. He led to the concept that the energy is quantized, at least the energy of a vibrating atom, and that energy depends on the frequency of the absorbed emitted photons. We came to the conclusion light comes in discrete little packages, particles called photons, and their energy was E equals hf. And that'll be our starting point for today. I should maybe review also. H was about 6.626. You can refer to previous lesson for, I think it's 6.626 times 10 to the minus 34, and the units were joule seconds to make the units match. So incredibly small, which makes sense because a photon is an incredibly small thing and shouldn't have an overwhelming amount of energy associated with it. So what is the photoelectric effect we've been talking about? Well, it turns out if you shine light onto metal, that metal is going to emit or is going to eject electrons. Now, this doesn't happen with any light. So every metal kind of has its own little threshold where if the light has a high enough energy, it's going to emit electrons. So every metal will do this, but each metal is different. Some metals require really high frequency light, and some metals require low light. But this idea that metals, when light is shone on them, emits free electrons, can be observed, and we call it the photoelectric effect. It's kind of like loosely speaking, it's like your solar calculator. Kind of one example of this effect. Light comes in, free electrons are created that are available to provide a current, maybe run a small device or something. So I mentioned each metal has a different threshold. So we're going to call that the work function. So every metal's threshold, we're going to give that name a work function, and we'll talk about the work function in a second. And so unless the frequency matches that work function, it's not going to release electrons. And if photons of higher energy are incident on the metal, then that extra energy is going to be released in the form of kinetic energy of those electrons, and you get a current. So you might want to get this down just in the side space of your note. The photoelectric effect, you can just summarize it. It's the production of free electrons when a metal is exposed to light. So what we want to do next is actually play around with the photoelectric effect and just observe some of these things. So here is the setup for the photoelectric effect. Light hitting the surface of the metal, and in this diagram here, on my cursor. So what we have right here, what I'm pointing to, this is like a metal plate made of some kind of metal. And then you have some light shining in on it. And the electrons, symbol E, will be released. And we call these electrons, we give a special name. If these electrons are created with the photoelectric effect, we call them photoelectrons. So in this device, you can measure the current. So if the free electrons are created with some kinetic energy, there's a moving charge, they're going to create a current, right? And so in this device, you can measure the currents. And you also had an adjustable voltage. So you can see right now we have electrons being emitted from a positive plate and going to a negative one. So naturally, the electrons will want to, well, first of all, there was no charge on the plates, the electrons would just be free to move and they would just go fire off. But if you turn on some potential difference, you give this plate a positive charge and this plate a negative charge, an electron will actually want to go back to the positive charge. So it has to have enough kinetic energy to actually make it across the plate before it is turned around. So this voltage allows you to increase or decrease that potential difference to make it harder or easier for an electron to make it across the whole device. Yeah, that's everything I wanted to get with that one. So let's actually take a pause, and I have the link for this applet on our Brightspace at the very least. But it's a FET simulation on the photoelectric effect. It's really cool. So I'm going to run this. And so you can see right now, let's just refresh that. It seems to be running slowly. I've had it running for a while actually. So yeah, so we'll try looking at different types of metal. We'll vary the type of light that we're shining on the metal. It's a pretty cool applet to play around with. All right. So right now you can see that we are shining violet light, wavelength of 400 nanometers, onto sodium plate. So sodium is a metal. And right now you can see the intensity of the light is 0%. So actually there's like no light. But I can crank this up. You can see we're shining some light on that. And so now we have some electrons being produced. Now, one thing to notice is every electron doesn't have the same kinetic energy. Some of them have a higher speed than others. I might actually just make this just to get a bit more. I'm just going to crank this up. Some of them have more kinetic energy than others and move across faster. And what I can do is I can actually just show only the highest energy ones. So you can see right now, only the highest energy ones are coming across, and all these guys have the same speed. The first thing I want to kind of convince you guys of is if I reduce the intensity, I'm going to lower the amount of electrons, but they're going to have the same energy. So just if you can kind of mentally look at the speed they have, if I decrease the intensity to maybe 50%, so same light. So I'm not getting as many photoelectrons, but you can see they have the same kinetic energy. So this was a problem with the wave theory of light, because the wave theory of light said, if I have more intensity, then the wave theory would say, if I just keep increasing the intensity, I should keep increasing the energy of these released electrons. But this wasn't the case. It only affected it only affected how many were released. So again, another downside of the wave theory of light, couldn't explain this. So hopefully you're convinced that this UV light shining on sodium produces these photoelectrons. Let's look at, I'm going to show all of them. Let's drag it down a notch. So let's shine blue light on here. So blue light looks like it has enough, doesn't have enough as much energy as the violet light, but it's still producing photoelectrons. Let's try green light. So green light, lower energy, and it doesn't look like this green light has enough energy to emit any electrons. Yep, doesn't look like it. So I want to go back to blue light for a second. So if you'll notice that we're still emitting photoelectrons, but what do you notice about their top speed? It's actually less than the UV light. So when you have a higher energy light shining on, that extra energy is giving those electrons a higher kinetic energy. So something to keep in mind as well. The more energy of the photon, the more energy released as kinetic energy for those guys. So we've talked about intensity only affects the number, not their kinetic energy. But hopefully you're convinced that the higher energy of light gives a faster moving electrons. Now I'm going to actually just show the highest energy electrons for a second too. And you can see these electrons are moving, reaching the end, a current is measured. Now I'm just going to adjust the voltage. So you might be wondering, well, how was this threshold work function determined, or like how do you determine what frequency is going to give some photoelectrons reduced? Well, you can play around with this, what we call retarding potential. So retarding potential means you can actually retard the electron's motion a bit, make it harder to get across. So if I do that, I think I made it too hard. Oh no, yep, they're getting across. Might actually make the intensity of light a lot higher to see more. So let's get all these guys here. There we go. So right now, I'm making it a lot easier for them to come across, but if you can see, if I change the potential difference and switch it around, so now I'm making the negative plate over here and the positive plate over here, and you can see the positive symbol, the negative symbol. Make it a little smaller. I want to see if I can slow any of these down. Yeah, there we go. So you can see that some of the guys are making it across. Some of them just barely make it, but others don't have enough energy to get turned around. So you can vary this potential. You can just play with it until you get to the point where you can just tell that no electrons meet the other side, and you can tell that because the current's going to be zero. And from there, you can measure the work function of the metal, i.e., what frequency of light you need to actually get these photoelectrons. So I'm going to go back to our note. We're going to get a few things down on paper, but I encourage you, play around with this, play around with different types of metal. I think there's actually a spot where you can, given the, where you can play around and see what frequency of light gives the cutoff and actually like look up what metal it is. But I'm going to take a pause on the applet for now and come back to our note. All right, so hopefully you've kind of seen the experiment, kind of got an idea of what's going on with that apparatus. So what happens if the retarding voltage is set to 0? So there's no potential different across the plate. So what's going to happen, and there's 3 things you get to get down here. So because there's no retarding potential, if an electron is like released from the plate, it's going to have some kind of speed, and it's going to make it across. It might take a long time to make it across because, as you saw, some had a lot of kinetic energy and some just had a bit, and it took them a while to cross. But they're all going to make it across. So they all contribute to the current. And what we saw, that increase in the intensity of light increased the current because there was more electrons, but did not affect their kinetic energies. Those guys still moved at the same speed, but it increased the current because you had more of them. And I showed you there was some threshold frequency in which no photoelectrons were produced. So with our sodium example, we saw that violet light gave you photoelectrons with a lot of kinetic energy. Blue light gave you photoelectrons, and they had some they weren't moving as fast, lower kinetic energy. We saw green light didn't produce any. So somewhere in that range between green and blue was that threshold frequency. And I want to add just maybe one note. Actually, I think I have 2. So what V equals 0 means is that basically there's nothing slowing down the photoelectrons. They're all going to make it across. All these guys, whether they have a little speed or a big speed, they're all going to get across and contribute to the current. And I want to add a little note here. So I mentioned this little this threshold frequency F naught. F naught corresponds to the work function So we give it the symbol W. So work function of the metal. And later on, we get an equation quantifying the photoelectric effect. We will use a W for the work function. And the work function is given by H times F naught. So if you know that, so it's basically, this is the, remember HF is the energy of a photon, right? This is the minimum energy that you need to get photoelectrons. So this is the work function. All right, next up. So what happens if you give a retarding voltage that's greater than 0? So when it's when there is some voltage slowing down, only the highest energy. So if you recall, I played around the voltage, and we had an example where we had electrons with a lot of kinetic energy released. They made it across, while others got turned back. Maybe they didn't have enough kinetic energy coming off the plate, and so they got turned around. And then finally, when there's a certain voltage where if it's high enough, then all of the electrons turn back. So some of them might get turned back right away. Some of them might make it to the very end, but they get turned back too. So even the highest energy electrons are unable to make it across. And the purpose of showing you this is how that frequency was determined. This was how, because this is how the that work function was determined. So the last few slides have been an illustration of how we get that that special threshold frequency F naught and how we calculate the work function for various metals. It involves the setup and varying the potential. Okay, so 3 observations which from this photoelectric effect, which led to Einstein's theory of the photon. So the particle theory of light. So for a given metal and frequency of radiation, the rate at which photoelectrons are ejected, and hence the photocurrent, is proportional to the intensity of the incident light. So it basically means if you double the intensity of the light, so you're not doubling the frequency, you're just doubling like how many photons are shining on that metal, you're basically going to double the current. So for a given metal, there exists a certain minimum frequency of incident radiation, below which no photoelectrons can be emitted, and we call that the threshold frequency. So remember, for sodium, it was somewhere between green and blue. We had that threshold frequency, no photoelectrons. Number 3, for a given metal of particular work function, increase in intensity increases the magnitude of the photoelectric current, but the stopping voltage remains the same. So again, this just showed that if you had the certain stopping voltage, it just showed that the kinetic energy of all those guys is the same. Whether you had, if one electron can't make it with that stopping voltage, then a million of them can't make it. So even though the intensity of light produces more photoelectrons, the stopping voltage remains the same. It just means that the kinetic energy of those released electrons doesn't change, just the number of them. So what I have for you here, this is actually the equation governing the photoelectric effect. So I'm actually going to squeeze. You guys have more room on your lesson sheet if that's where you're taking notes. But I'm actually going to write a few things up here. So when we use this formula, you might be asking, well, what kinetic energy? Because there was lots of different. We saw photoelectrons can come off with a little bit of kinetic energy or a lot. This EK stands for the maximum kinetic energy of the photoelectrons. H is Planck's constant. F is the frequency of the incident light. That's the frequency of the light you're shining on it. And the work function, remember, work function was equal to H times F naught. And this is the work function. And so you can see if your frequency is high enough that it is more than the work function of the metal, then you're going to have some extra energy that goes into kinetic energy of your photoelectrons. So what does this graph look like? I'm just going to switch colors here. Dark blue. So EK equals HF minus W. Well, H is a constant, and for a particular metal, W is a constant too. So actually, this should just look like the equation of a line, and it does. So I'm going to actually draw it on here. So I'm going to call that minus W. It's like almost like the y-intercept. And then this graph is linear. I'm going to try to draw the best line I can. That's pretty good. And this is graphing the relationship EK equals HF minus W for different frequencies. So I have three cases. And the first case is when the frequency is low, and it's low enough so that it's not, so that HF is not more than the work function. So in this case, the first case, the energy of photons is less than the work function. So you get the energy of the photons, HF, is less than the work function. And so that the kinetic energy is less than 0. Well, that's what the math gives us, but that just is saying there's going to be no photoelectrons. You don't have photoelectrons with like negative kinetic energy. It's just saying you're not going to see any photoelectrons. So this is case 1. Case 2 is when they match perfectly. Case 2. So in case 2, the energy of the photons is equal to the work function. So HF is equal to W, and EK is going to equal to 0. So what that means is you're going to get photoelectrons produced with no electric or with no kinetic energy. So they're just going to be free electrons still on the metal. So photoelectrons with no kinetic energy. And the final case is when HF is more than the work function. So when that frequency is high enough. This is case 3. You have HF being more than the work function. So you're going to have EK being greater than 0. And so then you're going to have photoelectrons produced with some kinetic energy. Photoelectrons So those are the three cases. Either your light doesn't have enough energy, and it won't release any photoelectrons. The case where they perfectly match, you get the threshold frequency, you're going to have photoelectrons with no kinetic energy. And then in the case where you do get photoelectrons, you have to have the frequency of your light times H has to be more than the work function. And a couple things to note about the graph. Imagine you had another work function that was a higher work function than the one I drew here. I'm going to draw it with a graph line. Imagine what that would look like, because think about the equation. It'd be HF minus W. So different work function. H is still the same, right? So H would be the same, and you get a graph that looks like this for another metal. But the big idea is because this equation, EK equals HF minus W, changing the work function doesn't change H. And the slope of all these lines is H. So if you graph for any metal, graph this photoelectric effect equation, they're all going to be parallel lines with the slope of H. But the bigger the work function, the lower that intercept is going to be, and then the higher frequency you're going to need to get that energy above 0. All right, so that's a little mathematical analysis. So you guys are going to just play around with the photoelectric effect a little bit. So on your practice sheet, you do have a table of different work functions. Work function is generally given in terms of the electron volt. So again, this means that in order for photoelectrons to be produced, the photons of light have to have an energy of at least this much. So for aluminum, your photons have to have an energy of at least 4.2 electron volts. So it must have a certain frequency to have that energy. And you have the work function for various metals there that you can just use in any problem. And then here's our equations. So these first two equations, when you just combine them together, gives you the equation we had in the previous slide. I'll write this down too. So this is combining them. You get EK equals HF minus the work function. Of course, if you're not given the frequency, you're given the wavelength of a light, you can just rewrite this as EK equals HC over lambda minus W. Those are the same thing. And a reminder that for Planck's constant, I think I said 6.626, that for your work to those sig figs, you can just use 6.63 is fine for your work. So give those a try. The problems aren't, I don't think they're overly complicated, just kind of getting you used to using the equations. Nothing mind-blowing, but it would be definitely worth your while to play around with that applet and just, try to estimate what the frequency of light is for various metals. And for some of the problems you do, you hopefully actually be able to kind of like verify your results on the applet itself. So what's up next? So I've mentioned it before, but this what this photoelectric effect kind of illustrated is that light is a particle. These photons of light shone on this metal. We had little mini collisions with the electrons in the metal and like dislodged them. So it gave evidence and credence to the idea that light is a particle. So now we have seen that, we proved in the last day that light is a wave and has like wave-like properties. We can think of light as a wave, but we can also think of light as a particle too. In fact, it's both. And in fact, not only light has this wave-particle duality, all particles do. Which is kind of weird that we can find like the wavelength of like a particle like an electron. And our next lesson too, we're actually going to show that if light is a particle, it actually has momentum as well, which is pretty cool. So I'll save that till our next lesson. Until then, guys, stay well, have a great day, and we'll see you soon.